Okay, so now let's talk about how to actually find out if our proportions are really off or not, right? Are our proportions statistical outliers? Are they deviants? Are they significant, right? Do they stand out, right? That's what we want to know. And in order to do that, we're going to have to use a measure called the chi-square statistic. Instead of the t statistic, which looks at distance away in terms of standard error, instead of the f statistic, which looks at the proportion of the variance we're interested in over the variance we cannot explain, the chi-square does something different. It's now looking at expected values. What would we expect, and what did we actually observe, right? And so the chi-square is going to look like this, right? So be careful that you don't, usually it's like an uppercase X, and it looks a little bit different than like just a regular letter X. It's usually a little more curvy to let you know it's chi-square. So the chi-square is really going to be interested in the difference between what we observe, right? The actual observed frequencies or percentages minus the expected frequencies, right? So when we're looking at observed versus expected, this is what we see in our sample, right? And this is what we would predict given our hypothesized population. So this is that predicted population part, right? So we're interested in the difference between those two frequencies. Now, although you could use proportions as well, you can only do that if you have the same, if you have a constant number of items. So you probably are safer to go with frequencies because those are sort of like weighted proportions. So you probably want to go with that. All right, so we're interested in this difference. But remember, when we look at this difference, sometimes they're going to be positive, sometimes they're going to be negative. And so what we do here, as usual in statistics, is we square the whole thing, right? But we also want to know about this difference as a proportion of what was expected, right? And we want to do this for every category, for the number of categories. And I goes from 1 to the number of categories. And there's actually an I down here for everything. So what this is saying is that for each category, right, each proportion that you're looking at. So in our sort of toy example with the red, blue, and yellow, right? Blue, red, yellow, right? In this example, we would do this for blue, we would do this for red, and we would do this for yellow. So number of categories. So categories really speak to what are the proportions made of. And so in here we have 3 categories, so we would do this 3 times and add those proportions up. And we want to eventually be able to find the observed frequencies and the expected frequencies. Now, in the example that we saw with the voting for candidate A and B, one of the things I hoped you noticed was that the observed frequencies were given as just number of votes, how many people voted. But the expected frequencies was, hypothesized population, that was given as a percentage, right? So you can't subtract votes from percentage. You have to translate them both into something that's the same, right? And so in that, it's helpful to change the expected percentages into expected frequencies, right? And there's going to be another reason for changing it into expected frequencies instead of changing the observed frequencies into observed proportions. And I'm going to go into that a little bit later. So here's what I want you to think of this as. It's really the squared difference between observed and expected frequencies as a proportion of expected frequencies, right? And you want to do that, and you want to sum that over all the categories. Once you have that, then you get your chi-square value. Now let's think about this chi-square value. If this difference is very, very large, right? So observed frequencies are just very different than expected ones, right? If that difference is very large, you're going to have a very large chi-square, right? Also, if this difference is very small, they're really, really close to each other, then your chi-square is going to be very small, right? So chi-square is giving us a measure of how far apart the observed and expected frequencies are, right? Also, I want you to see that the chi-square cannot be negative. First of all, because we're squaring this difference, right? So this numerator cannot be negative. Not only that, but expected frequencies also cannot be negative because we're counting up how many things we have, right? How many things we observed. And so this also cannot be negative. So this whole thing cannot be negative. So already we see in our mind the chi-square distribution will probably be positive and positively skewed because it stops at 0. There's a wall at 0. Okay, so now let's actually talk and draw the chi-square distribution. So imagine having some sort of data set and taking from it over and over again samples. So you take a sample, and so you have this big data set, you take a sample, and you calculate the chi-square statistic, right? And you plot that. So you plot that. And then you put that back and you take another sample and you take the chi-square, plot it again. And do that over and over and over and over again. You'll never get a value that's below 0, right? And you'll get values that might be way higher than 0 sometimes, right? But for the most part, they'll be clustered over here. So you'll get a skewed distribution. And indeed, the chi-square distribution is a skewed distribution. Now here, when we look at this, you might think, hey, that looks sort of like the F distribution. And you're right. Overall in shape, it looks just like the F distribution. And in a lot of ways, we could apply the reasoning from the F distribution directly to the chi-square distribution. For instance, in the chi-square distribution, our alpha is automatically one-tailed. It's only on one side. And so when we say something like alpha equals 0.05, this is what we mean. We mean that we'll reject the null when we have a chi-square value that's somewhere out here or out here or out here. But we will fail to reject if we get a chi-square value in here from our sample. Now, this chi-square distribution, like the F and T distribution, it's a family of distributions. It's not just one distribution. The only one that is just one distribution is the normal distribution. The chi-square distribution, again, depends on degrees of freedom. And the degrees of freedom that the chi-square depends on is going to be the number of categories minus 1. So if you have a lot of categories, the chi-square will look distribution will look different. If you have a small number of categories like 2, the chi-square distribution will look different. All right, so let's talk about what alpha means here. The alpha here is the set significance level. We're going to say we are going to use this as a boundary, a cutoff, so that if we have a chi-square from our sample that's bigger than this boundary, right? Then we will reject the null, right? What is the difference now with p-value? Now the p-value says this is the probability. So we might have a p-value somewhere out here, or we might have a p-value somewhere here, right? The p-value is going to be very similar to other hypothesis tests, what the p-value means, and other hypothesis tests. Basically, it's going to be the probability of getting a chi-square value larger, more extreme, right? And in this case, there's only one kind of extreme, positive. Larger than the one from our sample, but under a condition. Remember, in this world, which one is true? The null hypothesis is true. Given that null hypothesis is true. So considering if the null hypothesis were true, this would be the probability of getting such an extreme chi-square value. One that's that large or larger, right? That's what we mean. So in that way, the p-value is from our data, while the alpha is not from our data. It's just something we set as the cutoff. Okay, so there are some conditions that we need to know before we use the chi-square. When we use the chi-square, you can't just always use it. There are conditions that have to be met. So one of the conditions of the chi-square is this. Each outcome in the population falls exactly into one of a fixed number of categories. So every time you have some sort of case from the population, right? So let's say we're drawing out votes, right? Each vote has to fall into one of a fixed number of categories, right? So if it's two candidates, it's always two candidates for every single voter, right? So we can't compare voters that had two candidates versus voters who had three candidates, right? Also, these have to be mutually exclusive categories. One vote cannot go to two candidates at once, right? So they have to be mutually exclusive. You got to vote for A or vote for B. And you can't opt out either. They can't vote for nobody. Or else nobody has to be one of the fixed number of categories ahead of time. Okay, so the numbering is slightly off here. But the second condition that must be met is that you must have a random sample from your population. That's just like all kinds of hypothesis testing, though. Okay, number 3. The expected frequency in each category. So once you compute all these expected frequency in order to compute your chi-square, that needs to be each cell, each square, needs to have an expected frequency of 5 or greater, right? Here's why. You need a big enough sample, right? If you have too small of a sample, you're going to get expected frequencies less than 5. Also, you need big enough proportions, right? So let's say you want to compare proportions that are like, like one candidate is going to be predicted to win 99.999% of the votes, and the other candidate is only supposed to win 0.001% of the votes, right? And you only have 5 people in your sample, right? And so you need to also have big enough proportions, and these balance each other out. If you have a large enough sample, then your proportions can be smaller. Also, if you have large enough proportions, then your sample could be smaller, right? So they sort of play off of one another. And the final condition is not really a condition. It's just sort of something I wanted you to know as a rule. The chi-square goodness of fit test, so that's all we've been talking about so far. This test actually applies to more than 2 categories. You don't just have to have 2 categories. You could have 3 or 4 or 5 or 6, but they do need to be mutually exclusive, and each outcome in the population must be able to fall into any one of those. Okay, so those are the conditions.